Today we're going to work on Lesson 2, Unit 5 in your books. This is Investigation 4, and it's time for the second set of exponent rules. So you should be on page 332 in your books, and this is going to go all the way to page 334. The first part of this section applies a rule that you already know to fractions. So when we talked about power to a group, you take it to every single piece of the group. We're going to do the same thing when we talk about fractions. So number 1a, the first example is 3/5 to the third power. And what happens here is you take the 3 to both the 3 in the numerator and the 3 in the denominator. So x is equal to 3 and y is also equal to 3. The reason why this makes sense is that every time you have an exponent, you're going to take the base, which is in this case 3/5, and you're going to write it out the number of times that it says right here. So it says 3 times, the power is 3, so I'm going to write out my base 3 times. And then I'm going to multiply. When I multiply 3 times 3 times 3, that's equivalent to 3 to the third. And when I multiply 5 times 5 times 5, it's equivalent to 5 to the third. And later on, you're going to learn that you can go ahead and simplify that. So this will become 27 in the numerator, and in the denominator, we'll get 125. Let's look at the next example. Example B, we have c over 5 to the power of 2. And again, this would look like c over 5 multiplied by c over 5 because the exponent tells us to write the base 2 times. When you multiply c times c, we get c squared. 5 times 5 is 5 squared, or 25. So we get in this case that c to the second is equal to c to the power of x. So x equals 2. And 5 to the power of 2 is equal to our original 5 to the power of y. So that means that y is equal to 2 as well. Letter C, 4 over n to the power of 5. So let's follow the rule. The 5 goes to the 4, so x must equal 5, and the 5 goes to the denominator, so that means that y must also equal 5. And if you would write it out, the base should be written out 5 times. 3, 4, and 5 times. And hopefully you can see that this is equivalent to 4/5, and this is equivalent to n to the 5th power. And I don't know why I have that written there. Let me fix that. That is a 4. It should be an n. So n to the power of y. All right, next example, 1D. This one is a little bit more complicated. It's the same idea. We take the power to both the numerator and the denominator. So we have c squared gets a power of 3, and n also gets a power of 3. And then we need to use a rule that we've learned in the past. And the rule here is power to a power, you multiply. So 3 times 2, we get 6. And in the denominator, we have n to the third power. So in this case, x is equal to 6, and y is equal to 3. N is not equal to 0. The reason is that if 0 were in place of n, and let's say that we used our power of 3, 0 times 0 times 0 would give us 0. And if you have 0 in the denominator, it causes an issue. Because if you take any number and you divide it by 0, it's undefined. Because you can't take a certain number of items and divide it into 0 groups. It's impossible. So you can't have 0 in the denominator. So they just gave this problem a stipulation: n cannot be equal to 0. All All right, now it's time for a new rule. The last one was just an application of a rule that you had learned previously. And in this example, we're going to learn a new rule. Example 3a, 2 to the 10th power over 2 to the 3rd. In this case, we want to write out what 2 to the 10th is equivalent to. The power tells us how many times to write the base. So I need to write the base 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. And then down here, the power again tells us how many times to write the base. So I write it 1, 2, 3 times. Anything over itself is equivalent to 1. 2 divided by 2 is equal to 1. So that becomes 1, and we can say that it cancels. 2 divided by 2 also is equivalent to 1. 2 divided by 2 also equivalent to 1. So in the numerator, we are left with 2 times 2 times 2 times 2 times 2 times 2. Hold on, we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, need one more. So in the numerator, we have 2 times 2 times 2 times 2 times 2, etc. And in the denominator, we are left with just 1. Because all of these are really being multiplied by 1. This up here in the numerator is also being multiplied by 1. So what will be left is that hidden 1. If you take this whole piece and divide it by 1, you are just left with what's in the numerator. 2 times 2 times 2, and then we need 4 more 2's. So we have 7 2's, so it's 2 to the 7th power. So z is equal to 7. Let's do another example. 3b, 3 to the 6th power over 3 to the 2nd. So the power of 6 tells us to write the 3 6 times, and then the operation between these 3's is multiplication. In the denominator, the 2 tells us to multiply the 3 by itself. So we wrote the 3 2 times. And then again, 3 over 3 is equal to 1. 3 over 3 is equal to 1. And I'm going to write this a little bit differently this time so you can look at the problem in a different manner. So I copied down the 4 3's that were not canceled. And then what I'm going to do is I'm going to multiply this by 1 and then by 1 again, because this 3 over 3 is equivalent to 1. So I put it here. And this 3 over 3 is also equivalent to 1, so I placed it here. Well, if you multiply this by 1, you will still have this. If you multiply this by another 1, you will still have this original piece. These are unnecessary, so we can just write this as 3 times 3 times 3 times 3, or 3 to the 4th power. So z is equal to 4. I hope that you're starting to see the pattern, a simpler rule that we could use instead of writing all of this information out. Keep thinking about what rule you could use as we complete 3c. 9 tells us to write out the base of 10 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. The 3 tells us to write the base of 10 out 3 times. 1, 2, 3. We follow the same process of simplifying. 10 divided by 10 is equal to 1. 10 divided by 10 is equal to 1. And again, 10 divided by 10 is equal to 1. So it's 1 times 1 times 1 times this whole quantity here. So 10 times 10 times 10 times 10 times 10 times 10. So that's 1, 2, 3, 4, 5, 6 tens. So that's 10 to the 6th power. So z is equal to 6. Now what I hope you have noticed is that what we could do is we could right away just subtract 3 from 9 and get our final exponent of 6. That would have worked for A and for B. So in A, 10 minus 3 equals 7. It's always the numerator's exponent minus the denominator's exponent. Numerator minus the denominator. In example B, 6 minus 2 would have given us the 4 that we were left with. And we already looked at 3C, how that worked. So now let's look at 3D. In 3D, we take 2 to the power of x, and we subtract 5, and we should get 2 to the 7th following our rule. Because it's always numerator's exponent minus the denominator's exponent. So it's x minus 5. Usually, I will keep these in parentheses because sometimes it can be confusing when one of these values is negative. A lot of students will make a mistake where they will only use the negative that was already in the problem and they'll forget to use the extra negative. They'll get mixed up. So it's good to keep these in parentheses. So I'm going to do that for the rest of this time. So the problem becomes x minus 5 must be equivalent to 7. So to solve this problem, we add 5 to each side. On the left side, negative 5 plus 5 cancels, and on the right side, we get 12. And if you think about the problem, if you want to check your work, you can go ahead and write out the problem 2 to the 12th over 2 to the 5th, and you could write out 2 12 times, etc., and you could write 2 out 5 times in the denominator, cancel, and then see what you have left to make sure that you have 7 left. All right, example E, we have 7 to the power of x, and that is in the numerator, and in the denominator we have 7 to the power of y. So we take the numerator's exponent and we subtract the denominator's exponent, and that should give us the new exponent. So x minus y needs to equal 2. Sorry. So we can use any combination of x and y as long as the result is 2. So we could say that x equals 5, and 5 minus what would give us 2. So hopefully you would know that that's 3. So we could have 5 minus 3, that would give us 2. We could also use 7 minus 5 would give us 2. 6 minus 4 would give us 2. 200 minus 198 would give us 2. So any combination of x and y that would give you a result of 2 will work. All right, the next example is b to the power of 5 over b to the power of 3. So you can just take 5 minus 3, and like you normally would, subtract, and we get a power of 2. So they're trying to show you through these examples that it doesn't matter whether you use numbers or you use a variable, the rule will work the same. As long as the bases are the same, you can follow the rule. So when the bases are the same and you're dividing, you subtract the exponents. It's the numerator minus the denominator. Okay, in this example, we have 3 to the 5th divided by 3 to the 5th. So this is 3 to the power of 5 minus 5. So that's 3 to the power of 0. If you remember from before, we talked about how anything to the power of 0 is equal to 1. I know it's been a while since we've talked about that, but anything to the power of 0 is equal to 1. And the reason this makes sense is because we have the same number over itself. And remember, anything over itself is equal to 1. 2 over 2, 3 over 3, negative 5 over negative 5, they all are equivalent to 1. 3,000 divided by 3,000, equals 1. So just the same, this is equal to 1. And then h, we take b to the power of x minus x. X minus x, again, would be 0, which leaves us with a value of 1.